Hello everyone. So, this is the last module or the module on analytical method that we will be talking about today. So, in this module is a very short module, it will consist of only 3 lectures. So, let me talk about what is meant by analytical methods. Analytical methods are energy based methods which help us to formulate the equation of motion of a system. So, as we have seen earlier that equation of motion of a system, which can be a single degree of freedom system, a multi degree of freedom system or continuous system, is the first step towards solving the vibration or dynamics problem. In other words, the first thing that we need to do to obtain the vibration response of a system is to derive the equation of motion of the system. So, all this while we have derived the equation of motion using D'Alembert's principle, which employs dynamic equilibrium by considering an inertial force. The inertial force is actually given as m into u double dot, that is mass into acceleration acting in the opposite direction to the direction of the motion, or I into theta double dot, which is the inertial moment which also act in the direction opposite to the rotational direction of the system or the body. Now, when we get into complicated system, using the D'Alembert's principle or the method of dynamic equilibrium becomes difficult. It is always possible to apply the dynamic equilibrium or D'Alembert's principle using D'Alembert's principle, but it is only that it gets complicated with a complex system. It is very easy for a simple system, it is very easy to understand for a simple system, but as soon as the system becomes slightly complicated, the implementation of the method becomes very difficult. I am not saying that the method will become incorrect, but the implementation or adopting the method of dynamic equilibrium becomes difficult, because dynamic equilibrium is a force based method or a vector mechanics based method. We have to keep track of the direction of the vectors or the force, the direction of displacements and acceleration, therefore, it becomes bit complicated. The method that we are going to talk about are energy based method. So, here we deal with the kinetic energy and the potential energy of a system, and we derive the equation of motion using the energies of a system, considering the system is undergoing vibration in its degree of freedom. So, this method being utilizing the energies which are scalars are much more easier to implement, though the maths behind this method, behind deriving this method is slightly complicated. Therefore, in all vibration textbooks and courses, people start perhaps with the dynamic equilibrium, which is easy to understand, but slowly move on to energy methods or analytical methods using energy equations to derive the equation of motion. In summary, in this technique or in this lectures, we will see how to use the energies of a system, the kinetic energy and the potential or strain energy of a system to derive the equation of motion of a system. This is more beneficial for complicated system. So, with this we will move on to the derivation of the problem. So, we should start first with the Euler Lagrange equation. This is a famous equation in name of the scientists Euler and Lagrange. So, this equation is a derivative of a principle called Hamilton's principle. So, Hamilton principle is a more generic principle and Euler-Lagrange equation is derived from the Hamilton's principle. I will not go into the mathematics because this involves slightly advanced mathematics which is beyond the scope of this course. So, we will directly write down the Euler-Lagrange equation. So, for any multi-degree of freedom system, for any multi-degree of freedom system, the Euler-Lagrange equation can be written in this form. So, the Euler-Lagrange equation for a multi-degree of freedom system is written in this form. This is the time derivative of del L by del U dot j. What is Uj? Uj is the jth degree of freedom. And Uj is the jth degree of freedom and U dot j is the corresponding velocity. So, for a n degree of freedom system, j is going to be 1, 2, 3 and so on till n. Okay. So, j is 1, 2, 3 and so on, where n is the number of degrees of freedom. Now, what is L? L is called Lagrangian. L is called Lagrangian. Which is nothing but T minus V, where T is the kinetic energy of the system and V is the potential energy or strain energy. So, all system may not have a potential energy, but it may have a strain energy, the energy that is in the spring due to the expansion and contraction of the spring and so on. So, I have already written that T is the kinetic energy and V is the potential or strain energy, and L, which is called Lagrangian, is nothing but the kinetic energy minus the potential energy. Now, you can appreciate this, that the kinetic energy is going to be a function of the degrees of freedom and the velocities. And you can also appreciate this, understand this, that the potential energy or strain energy is also going to be a function of Uj. Therefore, L, which is T minus V, is also a function of U and U dot j, where U dot j is the velocity. Therefore, I can always perform this partial derivative of del L by del U dot j and del L by del Uj. I can always perform this derivative because L is always a function of u j and u dot j, and similarly this L is a function of u j and u dot j. Therefore, I can always take this derivative, and therefore, I can easily derive the left hand side of this equation. And let me repeat this again. The kinetic energy can be of a system, of a multi degree of freedom system, can be obtained in terms of its degree of freedom u j and the corresponding velocity u dot j. The potential energy or the strain energy can be obtained in terms of the degree of freedom. Therefore, L can be obtained in terms of u j and u dot j, and therefore, these derivatives can be easily performed, and therefore, the left hand side of the equation can easily be obtained. What is the right hand side? What is meant by Q and C? That is of course a question. Q and C are the non-conservative forces. Let me clear this and write it again. So, let me first write down the equation of motion, the Euler Lagrange equation once. So, Q and C, I have said this to be the non-conservative forces. So, there is a textbook definition of non-conservative forces, but I am not going to get into that. I can simply say that non-conservative forces are the forces with which you cannot associate any potential energy or any strain energy per se. So, any force that is not conservative in nature is called a non-conservative force. So, if we now try to see that L, which is T minus V, V which is potential energy, so if we can, so I can always find out the kinetic energy, I can always find out the potential energy, and therefore, the Lagrangian, and I can always derive this equation, and this equation is actually going to give me the equation of motion of the end of system. So, this is the famous Euler Lagrange equation and is very commonly used to find out the equation of motion of a complex vibrating system. So, let us do some examples which will help us a better clarity of the equation. So, first let me take a very simple system. So, this is an example. So, this example will show us how we can use Euler Lagrange equation to get the equation of motion of a vibrating system. So, let us take a very simple system, a very basic 2 degree of freedom spring mass system, so that the concept gets clear with this simple example, and then we will take a complicated example. Okay. So, these are the expression for the kinetic energy and the strain energy or spring energy of the system. These are very straightforward, right. The kinetic energy is just mass into half of mass into velocity square, and the spring energy is just the spring forces, the conventional expression for the spring energy. So, we can see that we have obtained the kinetic energy in terms of the velocities, and we have obtained the spring energy in terms of the displacement or the degrees of freedom. Now, Lagrangian So, let us try to first find out the first term of this, of the left hand side of the equation. So, let us first try to find out this term of the equation. Let me see how we can do this. So, there are 2 degrees of freedom. So, j is going to be 1 and 2. So, j is going to be 1 and 2. So, let me write this as now for j equals to 1, what do we get? For j equals to 1, this equation is going to be d dt del by del u1 dot into the total kinetic energy, which is half m1 So, if I find out this derivative, this is going to be equal to d dt of, this is going to be m1 into u1 dot, that is it, and del this term del by del u1 dot into this is going to be 0. So, I have only this. So, this is going to be m1 into u1 double dot. Now, so let us look into the second term, that is del L minus del L by del uj, where again j is going to be 1 and 2, and that is going to be minus del t by del uj plus del v by del uj. Now, t is just a function of u dot j. So, this is going to go to 0. So, this part is going to go to 0, because t is not a function of uj, v is a function of uj. So, for j equals to 1, now for j equals to 1, we can write minus del L by del u1 is equal to minus plus del v by del u1, which is del by del u1 of half k1 If I take this derivative, how is this going to look like? This is going to become k1 u1, and this is going to become k2 u2 minus u1 and minus of it, this since I have minus u. So, this is going to be minus. So, this is what I get for j equals to 1. Therefore, for j equals to 1, the entire Euler Lagrange equation LHS is going to be m1 u1 double dot plus k1 u1 minus k2 u2 minus u1. This is the complete LHS that I have got for j equals to 1. What is on the right hand side? The right hand side is the non-conservative force. Since there is no non-conservative force acting on the system, the right hand side is equal to 0. I can rearrange this and write this as m1 u1 double dot plus k1 plus k2 into u1 minus k2 u2 equals to 0. So, this is my equation of motion 1 because for the first degree of freedom. So, this is for u1. Now, let us look what is going to happen for j equals to 2. For j equals to 2, the left hand side is going to be d dt of del t by del u dot 2 minus del L by del u2 is equal to q non-conservative in 2. What I have missed saying that this q non-conservative is going to be the non-conservating force in the direction of the degree of freedom of uj. So, when j is equal to 2, the non-conservative force in the direction of degree of freedom 2. In previous case, the non-conservative force was the non-conservative force in the direction of degree of freedom 1 or u1. So, now let us see what is going to happen. So, this is going to be d dt into del by del u dot 2 and then I have half m1 u1 dot square plus half m2 u2 dot square minus del by del u2 into the entire expression for now q and c is again equal to 0 because there is no non-conservative force acting in the direction of u2. So, therefore, this equation, let us derive this and see what is going to happen. So, this is d dt. If I take this derivative, then this is going to be just m2 u2 dot, right, rest everything is going to be 0. Then I have del del u2. So, that is going to be, so this is going to be so u2, this is going to go 0. So, this I have k2 u2 minus u1 and plus k3 u3 and that is equal to 0. So, therefore, this equation ends up being m2 u2 double dot minus k2. So, this is minus. So, sorry, this should be equal to plus because this is del L, L is equal to t minus v del t by. So, del t by del u2 is equal to 0. Therefore, del L by del u2 is minus del v by del u2. So, this should be plus. So, I have a plus here. So, k u2 minus u1 plus k3 u3 is equal to 0, which can be rewritten as m2 u2 double dot plus minus k2 u1 plus k2 plus k3 into u2 is equal to 0. So, this is my equation of motion 2 for u2. Therefore, I get two equation of motion, which is m1 u1 double dot plus k1 plus k2 u1 minus k2 u2 is equal to 0, and then I have m2 u2 double dot minus k2 u1 plus so this is the set of equation of motion I get. I can always write in matrix form as m1 0 0 m2 u1 double dot u2 double dot plus k1 plus k2 minus k2. This is the equation of motion. So, by using the Euler-Lagrange equation and the expression for kinetic energy and potential energy of the 2 degree of freedom spring mass system, we can obtain the equation of motion. You can check for yourself. This is the equation that motion that you will get by solving the system using the conventional dynamic equilibrium method or using D'Alembert's principle, and they match exactly same. So, we can derive the same equation of motion by using the energies instead of the force balance that we have done so far. So, this I hope has been able to clarify the understanding of Euler-Lagrange equation. In the next lecture, we will take a more complicated complex example of a vibrating system, and we will apply Euler-Lagrange equation to derive the equation of motion. Thank you.